Hello everyone and welcome. So in this video I'm going to show you how to use LockBox 3.7 cryptographic library. It is supported for Delphi and C++ Builder, and it allows you to use hash functions, symmetric and asymmetric key algorithms, cryptographic algorithms, and also it supports the digital signature feature. So we will demonstrate all of these today. So first of all, open the tools, get it package manager, and install the LockBox 3.7. So as you can see, there are two versions, but be sure to install this one, 3.7. Right? Once you install it, you will have the LockBox here, 4 components: T-hash, decoder, T-cryptographic library, and T-signatory. So if you have some other set of components, then you probably installed the wrong version. So in order to demonstrate all these things, I have created a small example here, and we will demonstrate, like I said, hash functions, symmetric and asymmetric key algorithms, and digital signature. First of all, I have created a video about using hash functions within the component previously, so you can check it out also on my channel. And now I will pretty much demonstrate the same thing using the LockBox component. So if I run this application, let's say that I have this input message, and when I calculate its hash, I will get some hash value. So the point of hash functions is, well, it identifies the integrity of data. So pretty much this hash value should be unique for each input. In our case, for the input test, you will always need to get the same hash value. Okay, in this case is this one. So if I delete it and calculate again, then I got the same thing. So I will always get the same hash value. And that's the point. Also, regardless of the input, meaning its length, the hash value should always be fixed length. Okay, this can be input of 4 characters, 10, 100 million, or it can be a file of several gigabytes. It doesn't matter. The hash would always be the same length. Okay. Also, hash functions are not cryptographic functions, meaning once you calculate the hash of some message or file, there is no way to reverse to get the original message from the hash value. So that is not possible, and that's not the intention of hash values. So intention of hash is to identify the integrity, meaning, for example, let's say that you have an application that stores that simply needs to check the password if input password is correct, but you don't know the password itself. Usually the passwords are stored in some database and they are hashed, and when user inputs his password, you would calculate the hash of that password and compare it to the hash value that is stored inside your database. And if those two hash values are the same, then the password is correct. If they're not the same, then user, I guess, enter it incorrectly, and he needs to input it right again. Okay, so also you can use hash values in order to identify if a change happened. For example, you can calculate the hash value of a file, and once you calculate it, you can also determine if that value is changed afterwards, meaning if it's changed afterwards, then it means that the file was changed. So even the slightest change in input will result in a completely different hash, and that's actually great, because attacker cannot guess the content based on similarity. So in order to use hash functions with LockBox, you need to have the T-hash component, and you need to connect it to cryptographic library component, and it's simply done by selecting here this component, right? And also you need to select the hash function that you want to use. In our case, we will simply use the hash 256. It's completely okay. So that's just a matter of choice. You can use anything. And once I click the calculate hash button, Okay, this commented part is what you can assign in the object inspector itself. So if I click the hash1 component, you need to define the cryptographic library and the hash function. So that's pretty much what is done here. Okay, in order to hash the string, you would simply use the hash string method of the hash component. Okay, this component, it's hash string value, and output value would be stored here, hash output value property. Also, you can hash the file by using hash1, and let's say, okay, hash string. Okay, so you would load the file as a, for example, file stream, and you would hash that stream. Okay, so that is also an option. But like I said, please check out my other videos as well, because I have already covered the hash functions within the components, so you can check out that too. Okay, let's move on next. So symmetric key algorithms. So these are the algorithms that use one key for encryption and decryption. So let's say, let's run the application. So let's say I have some input, that's some secret message. It can be a simple text message, or it can even be a file. We'll see it later on. And we have one key, meaning when I encrypt this secret message with this key, and it's always recommended to have the key long as much as possible, and because it's then much harder to crack, right? When I encrypt it, I'll get some encrypted text. Okay, the point is, when I decrypt this text with the same key, I'll get the original message. Okay, so the procedure is, like I said, I encrypt this secret message with this key, and as a result I get the encrypted text. And then I decrypt the encrypted text with the same key, and I get the original message. Okay, so let's see how it's done inside the code. So this is how you would set the properties inside the code, meaning the hash, meaning the cryptographic algorithm, its chain mode, which I'll explain later. Pretty much password defines the key for the algorithm, and you would say encrypt string. Also, when you want to decrypt, also define key, password, and decrypt string. So encrypt string, decrypt string. Very easy. And let me just demonstrate one thing. When I encrypt string, I get this one. When I decrypt, I get the original. But watch this. When I click encrypt, it always generates a different encrypted message. So it's not the same. But the point is, whatever encrypted message is generated, the decrypted message is always the correct one. Okay? So why does it do this? Okay? One would expect, when I encrypt this message, original message, that I would always get the same encrypted message. And that's actually very dangerous. Let me demonstrate. So let's say that we have this original image, and we want to encrypt the image. So if we are using ECB chain mode, and that's, let me demonstrate here. So you see I've used the AES algorithm, but chain mode was CBC. If I would use ECB mode, ECB, I run the application, encrypt, decrypt, it's okay. But watch this, I got the same value, same encrypted value. So it will always generate the same encrypted value. And that's a problem. Why? Because if attacker knows that this part here means secret message, he can pretty much, based on that information alone, decrypt the parts of your message. Okay, but if you don't use the ACB mode, anything else, for example CBC, the initialization vector is always different, and he can never guess the parts of your message based on similarity. Okay, but regardless of the encrypted text, you will always, when decrypting, get the original message. So the same is here. When you have this original image, And if you encrypt it using the ACB, which means it doesn't use the random initialization vector, the attacker can pretty much presume what was the original message. Okay, but if you use any other mode than ECB, then look what you get. So attacker pretty much cannot see anything from here. He cannot presume the original message or the original image in this case. So, like I said, try to avoid the ECB mode and simply use CBC as a default or some other. Okay. Also, what we can do is to encrypt a file. So, for example, I have already prepared here a test.txt file. So it has 3 lines, and I will open it inside the notebook, Notepad++, and I will say encrypt the file. Then I'll choose it. Okay, and what happened? This test.txt encrypted was generated. I open it in Notepad, and this is what happened. Okay, I can encrypt the same file again. Now he generated this encrypted file, but that's because of the chain mode that we already demonstrated, right? But now let's decrypt the file. So I'll select the encrypted version of the file, meaning this one, and I'll encrypt it with the same key that was used for encryption. And now this file is generated, and as you can see, I got the original text. Okay, so now let's see inside the code how this is done. So pretty much when dealing with strings, you would use encrypt string, decrypt string, and when dealing with files, you would encrypt a stream, meaning you would load your file in, for example, a file stream. Okay, this is the original file, and this is the encrypted file where the encrypted version of the file will be stored. Okay, and when I want to decrypt, I pretty much use the same thing, but instead of encrypt, I use decrypt. So encrypt string, decrypt string, encrypt stream, decrypt stream, and that's how it's done. Okay, so that's the symmetric key algorithm. Like I said, it has one key, one for encryption and the same one for the decryption. Now let's see what are the symmetric key algorithms. So those are the ones that have a pair of keys, so public and private key. So you would, for example, publish your public key on a website, no matter where, and a person can send you a encrypted message using your public key. So he would encrypt it using your public key, but only you can decrypt the message using your private key. Okay, so in order to start using asymmetric key algorithms, first you need to generate public and private keys. In order to do that, you need to use this signature component, and that component also needs to be connected with the component that contains your asymmetric key algorithm. One of them is the RSA, okay, and pretty much LockBox supports generating public and private keys for the RSA algorithm, and that's the only algorithm they support. Okay, so how to generate these public and private keys? So again, this is the code that can be set inside the object inspector, and private and public keys will be saved into files. Okay, so I decided here to use memory stream, and this signature component, okay, this component here has the generate keys method. Okay, and once it generates the keys, I simply say store keys to stream. Which stream? Private key stream, and in that stream save the private part or private key, and store keys to stream into this public key, store the public part of the key, and save the file private key bin, public key bin, and show message keys are generated. So let's first generate the keys. That is the process that takes a long time. I mean, It depends on what version of the RSA algorithm you are using, and we are going to demonstrate the RSA on 124 bits. There is also it's also possible to use 248 or even 4096, so it's up to you. But when I click generate public and private keys, now we'll wait until those keys are generated, and like I said, it takes a long time, sometimes very few minutes to generate a key, depending on the asymmetric key size. But in our case, it shouldn't be that long, so we'll just wait it out. Okay, and keys are generated. And if I open the LockBox folder, I have here public key bin, okay, and I have a private key bin or binary, right? So, like I said, you can always share your public key anywhere, but private key is your own and you should not share it, right? So, and I have here an input message and I will encrypt it. So, pretty much encryption is done by using a public key, okay, and I get this as a result. And again, because of the chain mode, I have different values each time, but when I decrypt it, I will always get the decrypted message. So why would one use the asymmetric key algorithm instead of this one, asymmetric, right? Symmetric key algorithm is actually faster, but the problem is, how will you send the key to someone? You need to hide the keys somehow. So in order to do that, you would need to use asymmetric key algorithm. So you would encrypt the key itself by using a public key, and then send it to other person, and that person would decrypt this key by using its private key. Okay, so let me demonstrate how the encryption works. So encryption is done by using public key, and in this case I encrypt a string, and decryption is used by using private key and decrypt string. It's also possible to encrypt and decrypt a file using the same method, pretty much. Again, you have encrypt string here and decrypt string when dealing with strings, but when dealing with files, you are pretty much dealing with streams. So encrypt stream and decrypt string. And that's the main difference. Everything else is pretty much the same. So you see the code here, and you can check it out for yourself. Okay, so that's how it's done. And one last thing that we need to show is the digital signature. So what is the digital signature? Well, let's say that we are using this very same test.txt file, and we want to send it to someone. Okay, what we want to do is we want to digitally sign this file, meaning its content, so that when the person receives that file, that he can be sure that it's really something that we wrote, and it was not changed during the transmission or in any other way, or by hackers or something. So in order to do that, we can digitally sign this file, and using our own private key, okay, and then the receiver can verify that digital signature using our public key. So I have prepared an image here that shows how it's done. So if I have a file, in our case test.txt, I calculate the hash value of that message because it's unique, and once I have that hash value, I encrypt this hash value using my private key, okay, and that's digitally signed file, because once I've encrypted the hash value using my private key, I mean, nobody can encrypt that hash value besides me, because I'm the only one having that private key. Okay, so let's do that. First of all, you need to generate a set of public and private keys if you didn't already do so. But since we already done so, we have a private key and public key. So we'll skip that part. But it's the same procedure like when generating keys. It's the same code actually when generating keys for asymmetric RSA algorithm. So I can show the code. Okay, I already explained this code, but like I said, that is the code used for generating private and public keys for the digital signature. So what I'll do, I'll simply say this is the input file that I want to sign digitally, okay, and I want you to store my digital signature into this file, signature bin. Okay, so let's sign it. Document is digitally signed, and I have this signature bin. Okay, so what you would do next is send these two files, the message or the file and its signature, to someone else, and that person can verify if that signature is valid, meaning if that content inside this file was changed or not. For example, if I say verify signature, he said digital signature is valid, meaning that the content inside the file was not changed. It's what it was signed. But if I change this content, for example, I add small change here, then I say verify signature, now it's not valid. Okay, how does it know if it's valid or not valid? So, like I said, when you sign the document, you actually calculate its hash value, and then you encrypt that hash value using the private key. Okay, but the other person, what it does, it takes your file. Okay, it takes your file, it calculates its hash value. Okay, it gets hash value of the document or the message, then it decrypts your digital signature with your public key. Remember, here you have encrypted the hash value of the message using a private key, and in this case we decrypt that digital signature using a public key, and you'll get a hash. So the point is, when you decrypt that with public key, you get the hash, and if that hash value is the same as the hash value of the document, then your signature is valid. And if those two hashes are different, then this means that the content was changed. So like I said, digital signature is not valid because these two hashes are not the same. Okay, but if I delete the input, now digital signature is valid because the hash value of this content is now the same as the hash value of the digitally signed document. And let me show you the code. So when I use sign, what you actually are, like I said, when you are signing the document, you are doing encryption with your private key. Therefore, you need to load your private key from a file and simply say sign. Okay, and what are you signing? This document, and what is the destination? A signature, and signature is also a stream. Signature is also a stream. Okay, so that is the point. You need to load your private key. And then you simply, when you load your private key, then you simply use the sign method from the signature component. Okay, when you want to verify the signature, you load the public key. Okay, again, the image, because what you are doing, you are actually decrypting the signature, encrypted signature using public key. So you need to load the public key from a file, and you simply say signature verified. If it's pass, then it's valid, or else it's not valid. So these are the things that I wanted to show you today. So how to use hash functions, symmetric key, asymmetric key algorithms, and digital signature using LockBox components. LockBox components are free, so you can use them. And well, if you have any questions, like always, leave it in the comments. Thank you.